Welcome to EGR456. In today's class, we will talk about different sensors. And the sensors are very important because if you think about the UAV, we need to know the orientation, the location, airspeed, and all other different parameters. Sometimes we need to know the temperature, we need to know uh, the environmental conditions so that we are able to get the data from the environment and accurately control and navigate the UAV. So in this chapter, which is chapter 7, it's a fairly straightforward chapter. We are going to talk about multiple sensors that are used in UAVs. One thing it needs to be understood that these sensors are not super duper accurate. So they have their own limitations. They may have some errors in the scale factor. They may have some noise. So somehow we have to incorporate some type of filtering that would make use of all this sensor data and give us an optimal solution. And that will be the discussion in the next chapter. How do we take these noisy measurements and come up with the most optimal estimate on the solution? So let's start with what we are looking at. So when we looked at the architecture for autopilot and UAV design, we have the airframe. So this is where the airframe is. So this is the airframe. And in our case, the airframe is a fixed wing airplane. Now we integrate an autopilot which actually controls the control surfaces based on the commands. And now understand that you have these sensors. And these sensors could be accelerometers, could be gyroscopes, could be a magnetometer, could be a pressure sensor, could be a GPS. And it's interesting to observe that most of these sensors are present in your smartphone. So there have been some attempts where people converted the smartphones into an autopilot and use that to control the UAV. So, but these sensors, accelerometers, pressure sensor, magnetic sensor, gyroscope, and GPS, they are not high quality measurement sensors, which means because of the inherent effect that some either if defects or environmental effects, the measurement that you obtain from these sensors is going to be noisy. And that is where what you do is you have an estimator. So what estimator does is it takes all this noisy data and converts that into a consistent optimal solution. And this data is fed into the higher level controller that is making sure that the UAV is following the path that we prescribed. And again, the continuously it is sending out the commands to control the thrust, control the altitude, heading, and so on. And this information is continuously updated. What it means is the current position and the theoretical position of UAV is continuously compared and appropriate adjustments are made so that the UAV is tracking the path that we want to track. Now there are many sensors, but in this chapter, this feedback system, no, this is not a negative feedback system. A negative feedback system is typically you have a system, you have a comparison, you have an input, and so you have the feed. This is a negative feedback system. So when we looked at the autopilot, when we are trying to track, say for an example, this is what is the actual path. And if this is the desired path, the difference between these two is nothing but error. And that is used as the feedback to the controller, which is C. So this is the plant. And this is the feedback loop. So in the sensors, we talk about accelerometers, rate gyros, pressure sensors, magnetometers, and GPS. Nowadays, these are commonly used sensors. Sometimes they used cameras as well for vision-based navigation. And there's an entire chapter on vision-based navigation in our textbook. So what we are going to do is we are going to go step by step and look at the different types of sensors. So MEMS accelerometers are these teeny tiny sensors that are used to measure acceleration. And as you know, Newton's second law is force is equal to mass times acceleration, where force is the force acting on the proof mass, which is the mass that is suspended. This is the suspended mass. That is called as the proof mass. And you have spring on the either side. So this spring is spring in parallel. And as you can see that there is a capacitive pickup. What it does is as this mass moves forward and backward, the distance between the fingers changes. As the distance changes, the relative capacitance changes. And that capacitance change is used to measure the displacement, and that displacement is related to the acceleration. Now, one thing I want to clarify that MEMS sensor do not measure accelerations directly. What they do is they measure something called as specific force. And we'll talk about it in just a second. So MEMS accelerometers measure specific force. So I want you to look at the differential equation, which is given as mx double dot is equal to k in the parentheses y minus x, where what we want to do is we want to express this equation in the Laplace transform domain. So once I express this equation as a Laplace transform, please understand that I get this equation. So xs is the output and ys is the input. Now we talked about the Laplace transform, and this is nothing but the transfer function, open loop transfer function of this system. So m divided by k s square plus 1 is the open loop transfer function of this system. Now, I would like to spend a minute here and try to explore what happens when y is sinusoid. So y is the input and x is the output. In the Laplace domain, we don't have frequency. I mean, we have frequency, but it is expressed in terms of s. because it is expressed in terms of the Laplace variable. It is not expressed in terms of time. What I want you to think about, imagine if S is very small. If S value is very small, then what's going to happen is the quantity M divided by K, S square, will be approaching 0. What it means is whatever Y of S you have will be equal to X of S. In other words, when the frequency is low, then Y of S is equal to X of S. And what that means is the displacement that you observe is able to characterize the acceleration that is applied on the proof mass. And I will just spend a minute here just to talk about it. Now, what is the parameter that governs the behavior? The parameter that governs the behavior is how big or how small this M over K quantity is. And that is related with the natural frequency, which is square root of K over M. So what it means, if the frequency of the input excitation is very small compared to natural frequency, the system response is going to be flat. If frequency of the input excitation is very close to natural frequency, in that case, the system response is sort of going to be infinite. If the frequency, and I just want you to think about it, if the frequency of the input excitation is greater than the natural frequency, then you will have an attenuated response. And that what you can do is you can plot something called as the Bode plot. And Bode plot will tell you how the input versus output relationship changes with respect to change in the frequency of input. And some excellent videos on the Bode plot are pointed on the canvas as resources. So please take a look at those, and that would sort of give you an understanding of how the system behaves with respect to change in the input frequency. Now, one thing I want you to understand, that accelerometers, they are not free from errors. The accelerometers, they have some errors. So what type of errors exist in accelerometer? So there is something called as the scale factor error. Scale factor. Then there is something called as offset or bias. And there is some sort of noise. So these three types of errors exist in an accelerometer. And our objective is either somehow to minimize these errors so that the output of the accelerometer is very close to the input that we are receiving. So nowadays accelerometers are super teeny tiny, and you can get accelerometers. M over K defines the operating range of the accelerometer. So, and let me add this. So M over K. So M is the proof mass. So say kg. And K is the stiffness, which is Newton per meter. M over K. So that is nothing but, I just want to give you omega n, which is the natural frequency, which is K over M. and it controls the bandwidth. What it means is if you were to plot the body plot, you would notice the body plot, and this is K over M, which is omega n. So here omega n is equal to square root of K over M. And now if you think about it, what I'm going to do here is I'm going to change the value of frequency. So this is my omega axis. Initially my frequency will be 0, then it will be 0.1, it will be 1, it will be 2, all the way to the point that omega equals square root of K over M. At that time I have a spike, and this is the output divided by input. So you would notice when omega is significantly lower, the response is sort of a flat. And this is where I want my accelerometer to behave. Or this is basically called as the bandwidth. In other words, useful range where accelerometer can work. So, and the reason for that is, if typically in the MEMS system, the omega n is about 2500 hertz. And usually we use the MEMS accelerometer to measure the signals up to 50 hertz. And I just want to clarify what it means. Is think about that if you have an accelerometer and you have an acceleration, something like this, then accelerometer will measure this acceleration correctly. So measurement is going to be correct. Now imagine if you have an acceleration that is super duper fast, then this accelerometer is not going to give you response. It will give you some arbitrary response, which means when you have accelerations that are slowly varying, that are within the bandwidth of the accelerometer, your output is somehow related to input. But when your output or when your input is outside the bandwidth or the operating range of the accelerometer, you're not going to get a consistent or good measurement. So square root of K over M, or the natural frequency, is very important when you select accelerometers. So for an example, the accelerometers that you use for in UAVs, you won't be able to use for shock testing. So does that answer your question, Borna? Okay, if you look at MEMS accelerometer, this is something called as the die. So this is actually the silicon structure of the MEMS accelerometer. And you will never find a proof mass as a spring. But usually what you will have is, you will have comb fingers. So basically fingers that are like these. So you will see comb fingers, and then you will see mass attached to the comb fingers. So what you see here, these are the comb fingers. And there are movable fingers and there are fixed fingers. Fixed fingers are attached to the base. Movable fingers are attached to the proof mass. And what happens is, under acceleration, this proof mass can travel in X, Y, and Z direction. And that changes the capacitance, the relative capacitance. And what you see here are the circuits. These are all the circuitry, which is actually called very large circuit integration, VLSI. So these are capacitors, inductors, transistors, all other, and millions of those. What they do is they take this signal and convert that into a voltage or maybe PWM or something like that. As you can see, this is an analog devices chip, ADI. This is an ADI chip. That's why you see this is the mark on the die that shows who is the manufacturer of this chip. And this is called as the scanning electron microscope picture, SCM picture. So, and this is actually a MEMS device. So it is super duper small, but with SCM, what you do is you can actually magnify the picture and then see how this assembly is made. And again, there are interconnects, there are multiple transistors, and then finally what we do is this structure along with the support electronics is packaged inside some sort of packaging material that protects this structure from external shock, temperature, and other environmental effects. So a moment ago, I talked about accelerometers. MEMS accelerometers do not measure the acceleration. They measure something called as the specific force. And this concept is a little important to understand. So MEMS accelerometers measure the total acceleration minus the acceleration of the gravity. So this is something that you have to keep in mind. What it means is if you have a MEMS accelerometer and you place that accelerometer on a surface and the accelerometer is not moving, the surface is not moving, still you will observe that it's going to give you a G measurement. So here is what would happen. So consider that you have a MEMS accelerometer and you place MEMS accelerometer on a surface. And this is the sense direction. This accelerometer is not moving. So x dot is equal to 0, x double dot is equal to 0. But however, if you connect this, you will notice it's going to give you a measurement, say minus 1 G. And the reason for that is it's going to give you the difference between the total acceleration of the accelerometer casing minus the acceleration due to gravity. Gravitational acceleration is always going to be minus 1 G because gravity is always going to act in this direction and the accelerometer will always give you the difference. And that's why if you look at the equation for accelerometer, and these equations will come again and again when you look at the tracking applications, navigation applications, or applications related to AR, VR, or maybe using some sort of photogrammetry where you take pictures and use pictures for some measurements. So you have to remember this always, that the measured acceleration or the accelerations that is indicated by the MEMS sensors is the total acceleration of the accelerometer casing, total accelerometer casing minus the acceleration of the gravity. So that's why this acceleration is the difference between these two. And So how does this applicable in our case? So what it means is the accelerometers are going to measure linear acceleration, Coriolis acceleration, and externally applied acceleration. They will not measure gravity. What that means is, for an example, if you place an accelerometer and then this object starts moving. So the output of this guy will be the difference between the total acceleration minus the acceleration due to gravity. And that's what is the output gonna look like. So you mean number, yeah, Bernard, you mean numbers on this board? Or so the way you do it is, whenever you pick up an accelerometer, you look at the specifications. So for an example, ADXL is the analog device accelerometer, say ADXL 303. And what you do is, it will have specifications. It will tell you what is the scale factor, what is typically the bias. But the problem with these MEMS devices is, since they are manufactured using CMOS technique, every sensor is different, and that is because of the manufacturing. So what you will have to do is, once you get an accelerometer, you will have to perform something called as lab calibration, wherein you will perform thermal calibration. Then you will actually perform the scale factor calibration. Then you will perform the cross-axis calibration. And all this information will be used in your code or in your program to compensate for the accelerometer measurement. So it's a little bit involved, but for practical purposes, what you can do is, you can pick up an accelerometer and use the standard manufacturing tolerances and manufacturing specifications, and then it gives you reasonably good results. But if you want to have a very super accurate system, inertial navigation system or inertial tracking system, then you will have to calibrate it. So moving on, so just to emphasize what this means is, remember, accelerometers measure specific force, which is nothing but sum of non-gravitational forces divided by the mass. This is an important definition, and I want you to remember this. And the reason for these non-gravitational forces divided by mass definition is useful, because when we try to simulate, we already have the forces and the moments in X, Y, and Z direction. So all the forces, we subtract gravity, component of gravity from the applied forces, and that quantity divided by the mass is what is being measured by this accelerometer. So remember this is an important equation, and that will be very useful when we actually do some simulations and come up with the sensor models. So the accelerations that are measured is nothing but all the external forces that are applied on the system minus the gravitational forces or the component of gravitational forces divided by the mass. And I want to give you a very simple example. Consider that you have a smartphone here, and this smartphone has an accelerometer. And what you do is, you are pushing this smartphone, with force 1 Newton. And it is actually on this ramp theta. And this accelerometer, this smartphone has some mass m, and clearly you're going to have a component of mass mg, and if this angle is theta, this angle is going to be theta. So you're going to have mg cosine theta, and you're going to have mg sine theta, like this. So what it means is the component of the gravity is this guy. Now, question here is, what would be the acceleration indicated by this sensor? What would be the acceleration that is indicated by this sensor? And if this is a MEMS sensor, acceleration that is given by this sensor is 1 divided by mass, and all the forces. Let's look at the forces which are acting on this, which is 1 Newton minus the component of the gravity, which is m times g sine theta, and that would be measured by accelerometer. And this is important because now what I want you to think about is is like this angle, instead of uh, theta is equal to 30 degrees, just visualize if this angle is 0, or visualize this angle is 90. So now I want you to think about this. Now theta is equal to 0, which means the acceleration that will be measured by the accelerometer will be 1 divided by m. Now think about the, the, the angle to be 90 degrees. And then you will realize you will have sine 90 is equal to 1. So you will have m 1 over m in the parentheses 1 minus mg divided by the whole quantity will be divided by m, and that is what is the acceleration indicated by the sensor. Now, for a second, just imagine that this body is not moving. There is no force. So external force is 0. If the external force is 0, you will see that the total force that is acting on this guy is mg sine 90 divided by m. That is going to give you minus g. So your accelerometer is going to give you minus g. And you are welcome to try this with your cell phone. If your cell phone has an IMU app or inertial app, IMU app or inertial measurement app, or sensor data app, you can do this exercise fairly quickly and verify that your accelerometer is measuring the specific force, which is all non-gravitational forces divided by mass. That is what is being measured. And why is this important? This is important because now I want you to think about that you have this sensor that is attached, or it is located at the CG of the aircraft. And now when you have this tri-axis accelerometer at the CG of the aircraft, the accelerations will be the total forces, which is the lift force plus drag force, lift force plus drag force plus thrust force plus gravitational force minus gravity. So when you write down the equation for the acceleration measured, you will have to explicitly subtract this gravity to get consistent result. So this is super duper important. So remember this, accelerometer is going to measure the delta F, which is the difference between the total force and the component of gravity. Now let's see how this translates into the equations. First and foremost, if you look at the equations that we started deriving in chapter 3, and then we came up with the equations on the Genesis block, we had this equation. This equation is nothing but mass times acceleration is equal to force. And the acceleration has two components. One acceleration component is the linear acceleration, and the second acceleration is because of the Coriolis acceleration. So what this means is, think about that you have a mass that is going forward and also it is rotating. So you have actually two components of acceleration. You have the linear acceleration and the Coriolis acceleration. So this equation 1 is the equation that we are going to use. If you look at the expression for accelerometer, we just talked about it. Acceleration is the total force minus the component of gravity. So what I'm going to do is, I'm going to take this part of the equation and put it over here, and then subtract this component of gravity. Now this equation is a vector equation. So this equation is a vector equation. What does it mean? It means this equation actually has three components: one component in x direction, one component in y direction, and one component in z direction. So what I'm going to do is, I'm going to separate out x, y, and z component. And when I do that, when I collect the equation in x direction, this is what I get. When I collect the equation in y direction, this is what I get. When I collect the equation in z direction, this is what I get. So I have three equations. And it may be intuitive to look at these components shown over here. These components, they are part of the equations expressed on the Genesis block. The only difference is the component of gravity is subtracted. So basically, and depending upon the sign of the angles, so when I say sign, I mean SIGN of the angles, you will get positive or negative. So acceleration in x direction, you will add this component. Acceleration in y direction, this component gets subtracted. Acceleration in z direction, this component gets subtracted. So this is what is measured by the accelerometers when the accelerometers are inside the aircraft. I'll give you a moment to think about these equations. Once again, what these equations are: u dot is the acceleration in the body coordinate system in x direction. So this is the body acceleration in x direction. Then q, w, and r. So actually, if you look at p, q, r, p, q, r are nothing but the angular velocities about x, y, and z. U, V, and W are nothing but U, V, and W are nothing but body velocities. U is body velocity in X, V is body velocity in Y, W is body velocity in Z. PQR is the angular velocity in X, in Y, in Z. And again, these are all body. And you have these cross terms, which is P multiplied by V minus Q multiplied by U. All these cross terms, they are showing the coupling effect because of the rotation. So any question about this equation? If there are no questions about this equation can be implemented in an accelerometer model as shown. So as you can see, I have the additional terms, which are nothing but the noise terms or the error terms that are added into the acceleration equation. This is the actual measurement. And then these are the additional errors that come up. So a step back. We talked about a minute ago that the equation for accelerometer can be written as external, so total external forces minus the gravitational component. So I can use the same argument. So please observe here, what I'm saying is I'm expressing the equation in terms of forces. And you will see these forces are nothing but the lift force, the drag force, the thrust given by the motor. So these forces can be used to express the acceleration equations as well. And so which one is correct? So depending upon the formulation that you use, either one will work. But for simplicity, what we do is we use these equations. And it is very easy to implement these equations because please understand, we know Fx, we know Fy, and we know Fz. If you recollect, in forces and moments block in Simulink, we compute component of forces in X, Y, and Z direction. So we can directly use those forces and add or subtract the component of gravity, and that will give us the measurement of the acceleration. Any questions here? So one thing I need to clarify, this small m is the mass. And one thing you should keep in mind is these accelerometers, they are going to give you some output, but that will be contaminated, that will consist of errors and bias. So we have to use some sort of filtering algorithm that will fuse the data from multiple inputs and give us a consistent output. The next type of sensor that is commonly used is something called as the MEMS gyro. So gyroscope is used to measure the rate, and rate is given in radians per second or angular velocity. Most of the MEMS rate gyro, they operate on Coriolis principle. So what is the principle? So if you think about a MEMS gyro, if you apply and consider that this gyro is vibrating in this direction. So think about it, that there is a proof mass and you are exciting the proof mass in vertical direction. And all of a sudden, this entire sensor is rotated. If this sensor gets rotated, you will observe that in addition to the vertical oscillation, this proof mass will start oscillating in the horizontal direction. So that is because of the Coriolis effect. So as you can see that you have a proof mass and the proof mass is oscillated. It is actually oscillating close to resonance frequency. And then what happens is if you rotate or if there is external rotation, then you have off-plane oscillations. And these off-plane oscillations are because of the Coriolis effect. So let me show you how this gyro works. So this is again the die. The support electronics are not shown over here, but if you look at the way there are springs here, there are springs here, and what's going to happen is that this entire structure is oscillated in the horizontal direction. This entire structure is oscillated in the horizontal direction. But when you apply an external rotation, this structure, which is vibrating horizontally, will start vibrating vertically. And the magnitude of vertical oscillations are proportional to the angular rate. And that principle is used to characterize the rate gyro. And the modern gyroscopes are 3-axis, so you can measure the rate or angular rate in 3 dimensions, X, Y, and Z. But this is the principle. So you use Coriolis principle to measure the angular rate. So what type of error model is used for gyros? So if you look at the gyroscopes similar to accelerometers, they have a scale factor. So they have a scale factor. They have a bias, and they have some sort of noise. So the purpose of scale factor is, I just want to tell you, the scale factor gives you the relationship between the input and output. Bias gives you sort of the initial shift. This is bias. And if you look at the noise is something like, it's not going to be repeatable, but it will have some sort of oscillatory behavior depending upon the sensor characteristics. And if you have a 3-dimensional gyro, which means you have accelerometer, just like accelerometer, you have the 3-axis gyroscope, then you can measure the rate in the X direction, rate in the Y direction, rate in the Z direction. Please note, PQR are the body rates. So these rates are the angular rate of change of angular velocity in the body coordinate system. Again, you will have bias in X direction, bias in Y direction, and bias in Z direction. And then you will have external gyroscopic noise that is corresponding to that axis. Many a times, if you look at the gyroscope specifications, the noise floor or the noise limit in the X and Y direction could be different from Z direction. So you have to be careful of that. The next part is measurement of pressure. So why do we need to measure the pressure? There are two ways pressure measurement is useful. First of all, pressure can be used to find airspeed. So that tells me how fast or how slow the aircraft is going through the air. And it can be used to find altitude. Because as you know, as altitude increases, the pressure decreases. So if I have a differential pressure gauge, I should be able to find out the airspeed and altitude. So how does pressure measurement work? Pressure measurement principle is very simple. So you have a diaphragm. So you have a thin diaphragm, and on either side of the diaphragm, you have some pressure. So, and because if the pressure is the same on both the sides, the diaphragm will be flat. But if there is a differential pressure, if the pressure is different from one side and the other side, the diaphragm would bend. And because of that, there will be tensile and compressive stresses. And you will have something called as the piezo resistor. That means the resistance is going to change. It is something similar to a strain gauge. And that change in the resistance is an indication of how much that diaphragm is deflected. So the deflection of the diaphragm is calibrated with respect to the change in the strain, and finally that is related to the change in the external pressure. There are different types of pressure sensors. So as you can see, again, this type of pressure sensor does not have the attachment to attach tubes. So this sensor has attachment for one tube. This sensor this is used for pitot and static measurement. So you can attach pitot and static tube to these pressure sensors. But if you look at the pressure sensor, this actually comprises of the diaphragm, the electronics, support electronics, passives, all the capacitors, inductors, and the transistors. And again, what you do is you basically use these sensors on a PCB. You solder this onto the PCB and use the output of these sensors in your navigation and tracking solution. So how is this pressure sensor used to measure altitude? And if you look at from your thermofluids, the basic equation for hydrostatics is P is equal to H rho G. This is nothing but Pascal's law. H is height, rho is the density, and G is the gravitational acceleration. So this pressure sensor is going to measure H times rho times G. And you can use either ground as a reference, or you can use the standard atmospheric reference. If you use ground as a reference, the differential pressure, the pressure measured minus the pressure at the ground, is given as rho times G times H AGL. And this height can be found out by measurement of pressure. Nowadays, these pressure sensors are very accurate, and that can give you fairly accurate measurement. So if you are below 11 kilometers, so if you are below 11,000 meters, you can use a simple barometric formula where the pressure P is the pressure measured that is related with height by using this equation. PO is the standard atmospheric pressure, TO is the standard atmospheric temperature, and then GMR divided by LO. This is G is the constant, gravitational constant, m is the molar mass of the atmospheric air, and the gas constant. So you can use the gas laws to find out the height HASL. And the good news here is this actually takes into account the change in the density as the height increases. So basically, as you go up, the density, the air becomes less and less dense. As you are close to the ground, the air is quite dense. So change in the density of the air is taken into account with altitude and temperature. So typically we use this formula to find out the altitude. Now, if you look at the altitude measurement, uh, if you use the constant gas law, the constant density, or you can use the ideal gas law, you will have a very fair straight line representation and relationship between the pressure and altitude. But actually, it is not a straight line relationship. There is a curvature, and what we do is we use some sort of correction factor to compensate for these changes. But as far as UAVs are concerned, we will stick to our constant density assumption because the UAVs don't fly very high. The actual aircrafts can, or the fighter aircrafts can. So, but UAVs, they don't fly very at high altitude. They fly close to the Earth's surface. So we will use this constant density assumption. Now, how do we measure airspeed? Airspeed measurement is derived using the Bernoulli's principle. So if you look at the static pressure, this is the static pressure, and this is the dynamic pressure. If you look at the airplane, all the planes, commercial or hobby, you will observe that there is a small tube that comes out on the side of the plane. That tube is called as pitot and static tube. So this is the tube that is used. So what happens here? So basically this tube has two openings. One is connected on the back side of the diaphragm and one is connected on the front side of the diaphragm. So what happens is the diaphragm is going to measure the differential pressure. So when you have an air at velocity VA coming through the pitot static tube, as soon as it comes in contact with the diaphragm, the, the, the kinetic energy of the air gets converted into the pressure energy, and you are going to get a differential measurement of the pressure. And this differential measurement is used to find out the value of airspeed, which is VA. So with pitot static tube, you can find out the value of the airspeed. Any questions here? So these three are very important sensors. And next sensor that we are going to talk about is the magnetometer. Now, Earth has its own magnetic field, and Earth has a magnetic north, which is not aligned with the actual north. So there is some sort of angular difference, and that is called as declination. And what we do is we use a compass or a magnetometer to find out the yaw or find out the orientation. So if you look at the way the magnetic field is sensed by the magnetometer, nowadays we use 3-axis magnetometer. So what they do is the magnetometer is capable of measuring X component of the magnetic field, Y component of the magnetic field, and Z component of the magnetic field. Now what we need to do is this magnetometer is attached to the aircraft. Usually it is far away from the aircraft from all the ferrous and metallic surfaces, because the metallic objects or ferrous objects, they affect the magnetic measurement. So usually the magnetometer is away in the back, where the interference from the ferromagnetic surfaces is minimized. So what happens is this magnetometer is capable of measuring the magnetic field in the x direction, magnetic field in the y direction, and magnetic field in the z direction. And what we need to do is we need to use this information to find out the actual yaw orientation of the aircraft. Once again, as we talked about, magnetic north is not aligned with the actual north. There is some non-zero angle. And the bad news is that this angle changes depending upon latitude and longitude. So wherever you are on the face of the earth, depending upon your location, this value of delta is going to change. So you have to use the appropriate values of delta to make correction to your magnetometer. So how is it done? The good news is this magnetic declination variation is very well known and mapped. So depending upon where you are in terms of latitude and longitude, you can fairly certainly come up with the variation in the declination. So for an example, if you are here, somewhere here, then you can see that the magnetic declination is about -10 degrees, and you will use this information to correct your compass. So, and again, there are sophisticated software nowadays based on GPS, based on your longitude and latitude. It will give you the accurate magnetic information. So, and again, there is something called as Earth magnetic model, and this Earth magnetic model is implemented in the MATLAB. So you can actually use MATLAB toolbox, supply the values of latitude and longitude, and it will give you the magnetic declination. Also, there is something called as magnetic inclination, which is the variation about the pitch axis. So basically, this is the angle made by the compass needle with the horizontal at any point. So you have magnetic field variation not along the yaw, but you have magnetic variation along the pitch axis. So these values are used to correct the actual reading that comes out from the compass. So let's see how it is implemented in the digital compass or a magnetometer. So if you look at the heading means where the aircraft is headed, is the sum of magnetic declination and the magnetic heading. So the actual heading is nothing but delta, which is magnetic declination, and the magnetic heading. So magnetic heading is used or measured or determined from the measurement in the body coordinates. So what we do is we have this magnetometer, and then the measurement from magnetometer will allow us to compute the heading. So how is it done? Now please understand, we are going to map so magnetometer and magnetometer calibration is a completely different topic for an entire course. So there are multiple ways of calibrating magnetometer. A simplest way, you might have seen that sometimes your smartphone says rotate the smartphone in figure 8 so that it can sense the magnetic field around it and then compensate for it. There are something called as the soft ion errors. There are something called as hard ion errors. And these sophisticated chips and algorithms they are capable of compensating for soft ion and hard ion errors. And finally, what we do is uh, the raw measurement from a magnetometer is fed into this computational algorithms and these different uh, microcontrollers, and then a calibrated and corrected solution that comes out. And depending upon the algorithm, the gains are automatically tuned or gains are automatically changed. And again, there are different filtering algorithms too. So, but here we are going to look at a very simple approach wherein you have a magnetometer that is mounted on the aircraft and you get a magnetometer reading. And understand that magnetometer reading, so you have a magnetic field in the body coordinate and you have a magnetic field measured in the vehicle 1 frame. This is very important. Vehicle 1 frame. This is the body frame. And if you recollect how these vehicle 1 and body frame are related, if you look at the vehicle 1 frame and body frame are related with the roll angle and the pitch angle. So you have this roll angle and you have this pitch angle. So roll and pitch. So the rotation matrices that relate body to vehicle 1 is given by this rotation transformation. So what that means is if I really want to find out value of magnetic uh, heading, if I want to find out the value of magnetic heading, what I will do is I will get the measurement in the magnetic body. So M1X, M1Y, M1Z. Use the roll and pitch angles and get these values and use a tan to relationship to find out the magnetic heading. Once again, let me repeat. Now, consider the magnetometer. Magnetometer is attached to the aircraft. The aircraft frame is nothing but the body frame. Remember, we talked about the earth fixed, earth center frame, then we talked about the CG, then we talked about the vehicle 1, when we talked about the vehicle 2, then we talked about the body frame. Now, magnetometer is attached in the body frame. So whatever readings that you are going to get from the magnetometer will be in the body frame. So what we do is we take these body frame measurements and convert those to the vehicle 1 frame measurements. And then we look at the Y and X components of magnetic field in the vehicle 1 frame. And that gives me the magnetic heading. Everyone understood this? And some of you may ask me, where do you get these angles from? These angles are from either IMU or accelerometers. You get roll and pitch. The last sensor that is very commonly used nowadays is called GPS. So again, GPS, integration of GPS, the errors in GPS, and so on. That's an entire course in itself. But just to give you an idea, so there are 24 satellites, actually more now. They are orbiting Earth at altitude of 20,000 kilometers. And any point on Earth's surface can be seen by 4 satellites. And what happens is, if you have a receiver, you have radio signal that is coming from the satellite that is encoding the location of the satellite, the time at which the signal was sent. So what you can do is at receiver level, you can triangulate. So you can get the value of R1, R2, R3, R4. These are nothing but the pseudo ranges, and you can find out the 4 unknowns, which is latitude, longitude, altitude, and receiver clock offset. In other words, you are gonna get, you need minimum 4. You are gonna get the signal from satellite 1, satellite 2, satellite 3, and satellite 4. And with these 4 measurements, you should be able to find out the 4 unknowns. Most of the times, you have more satellites, so you are getting redundant measurement that improves the accuracy. But at the end of the day, with GPS, you should be able to find out the latitude, longitude, altitude, and time of the receiver. So you know where the receiver is, what is the time, and what is the latitude, longitude, and altitude is. There are many errors that you see in GPS. So if you look at the GPS, we use something called as pseudo range, because it's not the true range, it is computed from the measurement. And this pseudo range is affected by the multipath, the reflection, atmospheric errors, the stratification error, receiver errors, and the teeny tiny errors in the timing. So for an example, 10 nanosecond timing error will give you error of 3 meters in pseudo range. So what we do is we use sophisticated filtering algorithms like Kalman filtering uh, to compensate for the error in the GPS. So finally, what we do is we get measurement from GPS, we get measurement from accelerometers and gyro, and we fuse these 2 different types of measurements, and we try to come up with an optimal estimate. So if you look at the different types of errors that are observed in the GPS signal, you could have ephemeris data, you could have satellite data errors, multipath, receiver measurement, and you can have user equivalent error range that is affected by all these different errors. And because of the error, degree of dilution of precision changes, which means your measurement is gradually becoming less and less accurate. So as you can see that when the satellites are close together, you have high DOP. When the satellites are far apart, you have low DOP, and dilution of precision varies with time. And another thing important is, if you look at the total error of the GPS signal is given in terms of RMS. So typically the standard deviation is about 6.6 meter in northeast plane and about 9.2 meters in the height. So as you can see, the GPS is not super duper accurate, but what happens is the receivers, they actually used internal accelerometers, gyroscopes, multiple GPS receivers, and some additional information about where the receiver was, or where the receiver started, what was this initial position, to minimize these different types of errors. And what we do is we actually propose a Gus-Markov error model for the GPS error. And this model we will use when we look at the state estimation and correction in the chapter 8. So what we do is we have a noisy GPS measurement. So we have GPS, we have IMU, that is accelerometer and gyro and magnetometer. And what we do is we combine these two to come up with a good estimate. And that will be the topic of discussion in the next class and class after. How do we get good and accurate measurements when our readings are not so accurate? If you look at the way the GPS signal looks like, you will see that the error sort of behaves like a random walk, and you will see that your altitude error also behaves in terms of random walk. So with this, I'm going to stop here today, and I will be happy to answer any questions that you may have.